Good day and welcome to this video. This is the third and final part of the lecture video on parametric surfaces and surfaces of revolution. In the first part of the lecture video, we saw how surfaces can be represented by parametric equations or by vector-valued functions in two parameters. The second part of the lecture video dealt with parametrizations of surfaces of revolution. If you have not watched the first and second parts of the lecture video, please watch them first. In this video, we will discuss how to obtain the equation of tangent planes to parametric surfaces. Naturally, this will entail the notion of a derivative of the vector equation for the parametric surface. Let's start. Recall that parametric surfaces are the graphs of vector-valued functions in two parameters, say u and v. Suppose r of uv with component functions x of uv, y of uv, and z of uv is such a vector-valued function. Since r of uv is a function of two variables u and v, we will talk of the partial derivatives of r with respect to u and v. The partial derivative of r with respect to u, written in this manner, is the vector-valued function defined by the limit of r of u plus delta u v minus r of uv all over delta u as delta u approaches 0 if the limit exists. Note that subtraction here pertains to vector subtraction, while division by delta u here means scalar multiplication of this vector by the scalar 1 all over delta u. The partial derivative of r with respect to v is defined analogously. That is, it is the vector-valued function given by the limit of r of u v plus delta v minus r of uv all over delta v as delta v approaches 0 if the limit exists. I hope that these definitions of partial derivatives of r come as no surprise. The following theorem, which is easy to show, states that the partial derivatives of r with respect to u and with respect to v can be obtained, respectively, by taking the partial derivative of each component function of r with respect to u and with respect to v. That is, ru of uv equals xu of uv, yu of uv, zu of uv, and rv of uv equals xv of uv, yv of uv, and zv of uv. Now that we know how to obtain partial derivatives of vector-valued functions, we are ready to find equations of tangent planes to parametric surfaces. The next theorem is our main result for this lecture. It tells us how to identify a normal vector to the tangent plane of a parametric surface S. Suppose r of uv is a vector equation of S such that the partial derivatives of r with respect to u and with respect to v at u0, v0 exist and are non-zero. Then, the cross product of ru, u0, v0 and rv, u0, v0 is a vector that is normal to the tangent plane to S at a point on S corresponding to u equals u0 and v equals v0. We provide an outline of the proof of this result. Suppose the vector r of u0, v0 has components x0, y0, and z0. This means that the point x0, y0, z0 lies on the surface S, as shown on the figure on the right. Here, surface S is colored yellow. If we set v equals v0, we obtain the constant v curve r of u v0 on S passing through the point x0, y0, z0. In the figure, r of u v0 is represented by the green curve on S. Note that r of u v0 is a vector equation in one parameter u. Since we assume that the partial of r with respect to u at u0, v0 exists and is non-zero, then from Math 22, we have ru at u0, v0 to be a vector that is tangent to the curve r u v0 at the point x0, y0, z0 in the direction of increasing u. Analogous arguments show that the vector rv u0, v0 is tangent to the constant u curve r of u0, v on S at the point x0, y0, z0 in the direction of increasing v. In the figure, the tangent plane to S at the point x0, y0, z0 is colored light blue. Clearly, representations of the vectors ru u0, v0 and rv u0, v0 with initial point at x0, y0, z0 should lie on this light blue tangent plane. This implies that taking the cross product of the vectors ru u0, v0 and rv u0, v0 yields a normal vector to the light blue tangent plane. This completes the proof. We illustrate what we have learned in this video in the next two examples. For the first example, we are being asked to find an equation of the plane tangent to the surface S defined by the vector equation r of uv with components sine v, v minus 1, e to the u at the point where both u and v are 0. Recall from Math 22 that you need two information to determine an equation of a plane. Those are a point on the plane and a vector normal to the plane. We start with the point on the tangent plane. The point of tangency is obtained by computing for r of 0, 0, which is the vector with components sine 0 equals 0, 0 minus 1 equals negative 1, and e to the 0 equals 1. Hence, the point of tangency is the point 0 minus 1, 1. The previous theorem tells us that the vector normal to the tangent plane is the cross product of ru 0, 0 and rv 0, 0. Hence, we need to compute first for ru uv and rv uv. To find ru uv, according to our previous theorem, all we need to do is to take the partial derivative of each component of r of uv with respect to u. Hence, the components of ru uv are 0, which is the partial derivative of sine v with respect to u, 0, which is the partial derivative of v minus 1 with respect to u, and e to the u, which is the partial derivative of e to the u with respect to u. Similarly, our VUV has components cosine of v, 1, and 0. Don't be too eager to take the cross product just yet. Note that if we take the cross product of RUUV and RVUV, we will get an expression involving u and v. It is better to evaluate first both partial derivatives at 0, 0. Thus, we get Ru at 0, 0 is equal to the vector with components 0, 0, 1, and Rv at 0, 0 is equal to the vector with components 1, 1, 0. Now, we take the cross product of Ru 0, 0 with Rv 0, 0. We get that a normal vector to the tangent plane has components negative 1, 1, and 0. Finally, since minus 1, 1, 0 is a vector that is normal to the tangent plane, and 0, minus 1, 1 is a point on the tangent plane, we obtain an equation of the tangent plane to be negative 1 times x minus 0 plus 1 times y plus 1 plus 0 times z minus 1 equals 0, or, which when simplified is minus x plus y plus 1 equals 0. For the last example, we are being asked to find a vector equation of the normal line to the surface S with vector equation r of uv equals u squared, v squared, u plus v at the point 1, 4, 3. Recall from Math 22 that to find a vector equation of a line, we need a point on the line and a direction vector of the line, which is a vector parallel to the line. We are actually given a point on the normal line, which is the point 1, 4, 3 on the surface S. It follows from our theorem that a direction vector to the normal line to S is the cross product of Ru u0 v0 and Rv u0 v0, where u0 v0 are the parameters corresponding to the point 1, 4, 3 on S. Hence, we start by identifying the parameters u0 and v0. To do that, we equate u squared with 1, v squared with 4, and u plus v with 3. Hence, we get a system of 3 equations in 2 variables, u and v. From u squared equals 1, we get 2 possible values for u, which are plus or minus 1. Also, v squared equals 4 implies v is either plus or minus 2. However, from these possible values of u and v, only u equals 1 and v equals 2 will satisfy u plus v equals 3. In other words, u0 equals 1 and v0 equals 2. We now compute for RUUV and RVUV. The components of our UUV are 2u, 0, and 1, which are the partial derivatives with respect to u of u squared, v squared, and u plus v respectively. Similarly, the components of our VUV are 0, 2v, and 1. Thus, RU12 is the vector with components 2, 0, 1, while RV at 1, 2 is the vector with components 0, 4, and 1. Taking the cross product of RU12 and RV12 gives the vector with components 0, minus 4, or negative 4, 1, minus 2, which is negative 2, and 8 minus 0, which is 8. Thus, the normal line passes through the point 1, 4, 3 and has direction vector negative 4, negative 2, 8. Therefore, a vector equation of the normal line is given by the vector r of t with components 1 minus 4t, 4 minus 2t, and 3 plus 8t. To check whether you have understood the lecture videos, I urge you to try the following exercises on your own. We have now reached the end of the lecture video on parametric surfaces and surfaces of revolution. My name is Manuel Joseph Loquias, and I wish you the very best as you continue your journey in Math 23. Goodbye!